Okay, so hello friends, welcome to our online course on detection and estimation theory. And here in this lecture, going to talk about optimization. So I will do optimization in two parts. In the first part, I'll talk about general optimization. And in the second part, I will specifically talk about convex optimization and how to solve it. Okay, so let's get started with the optimization thing. So what is optimization? What do you mean by optimization? Optimization is you want to either minimize or maximize some function. Okay, so either you want to maximize, you want to find out the maxima of that function, or you want to find out the minima of that function. Okay, so you want to figure out either one of these two things from a function. So let me draw a function which may look something like this. So this is your function. Let's say the function is of a single variable x. Okay, so we have got this graph, and now you can have a function which may be something like this. Okay, now in this kind of a function you can see that there will be lot of minima points. So this is one minima point, this one is another minima point. Okay, so this one is minima point, this is another minima point, and if you okay, and there could be many other minima points. So these are minima points. What about maxima? So these are the maxima points. Now you can see that in a particular function fx you can have multiple maxima points and multiple minima points. Okay, now let's do a quick revision of what we used to do in our high school to figure out the maxima and minima of a function. So suppose if I give you a function f of x, and let's say if I want to find out the maxima of this function f of x, then what you used to do is you took the derivative of this f of x, so dfx over del x, you took the derivative and then you equated it to 0. Now what do you mean by taking the derivative of this? The derivative means you want to figure out those points where the derivatives are 0. So these are the points that you are going to get by solving this equation. Okay, now if you got multiple such points, so you got x stars, multiple of them where your derivative is going to 0, then what you used to do to figure out a minima point or a maxima point is that you figured out the double derivative of f of x. So you figured out this double derivative. Okay, you took the double derivative. Okay, and you checked whether this is greater than 0 at x star or less than 0. Okay, you try to evaluate. So if it is greater than 0, you set it to be a minima point, and if it was less than 0, you said that that particular is a maximum point. Okay, I hope you did all these things in your high school and you are familiar with these concepts. Now the question here is, if I'm given such kind of a function where there are multiple minima or multiple maxima points, then how do you figure out a point with the most minimum value? So suppose in this kind of a graph, in this kind of a function, I have two minima points. Okay, so you can see here we have one minima point here and one minima point here. So what I am interested in is to rather not find out a local minima but a global minima. So there are two kinds of concepts here. One is called as a local optimal point. The other one is called as a global optimal point. Now, what is a local optimal point? Local optimal point is in its neighborhood, it attains that optimal value. So it is in the neighborhood. While global optimal point is one, it is minima or maxima over the entire domain. Okay, so this is either maxima or minima over the entire domain. Okay, so you can see here I have not drawn the graph fully, but you can see if I were to be constrained in this particular domain. Okay, let's say if I make this as my domain of interest. Okay, then my maxima point, the global, this is my global maxima, and you can see here this one I can call it as a global minima. Okay, so this is a concept which everyone should understand. So the concept is global and local maximum and optimal points. Okay, now let's take one more example to understand what is an optimization. So let's take this example of a parabola. So suppose fx is x square plus 2x plus 3. So I want to find out a minimum of this. Okay, so I want to find out minima of f of x. Now let me first draw f of x, how it is going to look like. So this is my x-axis and this is f of x, and x square plus 2x plus 3 is going to be a parabola, and it is going to look something like this. At x is equal to -1, it attains a minimum value, and this value is equal to 4. Okay, you can verify that. Okay, and okay, so this is what is the minimum value, and on the either sides it is going to increase. Now how do you figure out this minimum value? How do you figure out this minimum value? Is you take the derivative of fx with respect to x equated to 0. So this implies you get 2x plus 2 is equal to 0. X turns out to be -1. So this is the point where the derivative is equal to 0. Now I have to verify whether this point is a maxima or a minima point. So what I do is I take the double derivative of it with respect to x, and this is equal to 2. You can see this is greater than 0 at all values. At rather all values, I should say at x is equal to -1. So x is equal to -1 is a minima point. Okay, and what is the value of this function at this point? F of, let's say this is x star. So value of function at x star is equal to, you can put -1 in this equation and you get 4. Okay, so this is a small example from what we know from our intermediate school, right? Now let's take one step forward and let's try to constrain this. So this is called as an unconstrained optimization problem. So if you do not have any constraints, so now two types of optimization problems are there. So one is called as constraint optimization. constrained optimization problem. The other one is called as unconstrained optimization problem. Okay, so in constrained optimization problem, in unconstrained optimization problem, you do not have any constraints, while in constrained optimization problem, you have some constraints. So let's take another example to show what is a constrained optimization problem in this. So suppose example number 2 is, suppose if I want to again minimize this function fx, we'll take the same function. F of x is x square plus 2x plus 3, and let's try to minimize this function f of x for all values of x which are, let's say, greater than equal to 0. Okay, so this is a constraint that I have introduced. So this is my constraint. What the constraint does is that it modifies, so it does is that it modifies the domain of the problem. Okay, so what does a constraint do is it modifies the domain of the problem. So let me just draw it again and show you how the function is going to look now from this perspective. So again, our function was something like this. This was -1, this is x, this is f of x, and now my function is valid only for x greater than equal to 0. So my function is going to be only this part. So my function is valid only in this domain, x greater than equal to 0. Alright, so now how do you solve such kind of problems? We cannot solve it using uh, our theory of just figuring out the derivative equal to 0 and then solving it. Okay, so we require some more methods to solve such kind of problems. And in this particular lecture, what we are going to do is we are going to try to understand different types of optimization problems and how do you differentiate between the different types of optimization problems. And then in the next part, I'll show you how to solve such kind of an optimization problem. Okay, so let me now write a very general form of an optimization problem. So let's take a general optimization problem. Okay, so in an optimization problem, you would either, so I'll take a minimization problem. You can obviously take a maximization. It could work in one and the same way. So what I will do is in this course, I'll talk about only the minimization. What you can do for maximization is that, so if I have, let's say, minimize f of x, suppose you want to maximize f of x, suppose you have this problem, you can convert it into a minimization problem by minimizing minus of f of x. So if you do this, these two problems are equivalent. Okay. So in this course, what I'm going to do is that I want to minimize some function of fx, and then subject to certain constraints. Constraint could be, let's say, fi of x is less than equal to 0 for I goes from 1 to m. So these are m constraints, m inequality constraints, and you can have some equality constraints also. So let me write them as hi of x equal to 0. I maybe go from 1 to n, or rather let me take another variable 1 to p, and these are called as p equality constraints. Okay, So what we are looking at is that we want to minimize this function f of x subject to certain constraints fi of x less than equal to 0, and there could be some equality constraints also. You might be wondering, I have not written constraints such as these, fi of x greater than equal to 0. Well, this is equivalent to writing minus of fi of x is less than equal to 0. Okay, so these two are equivalent, so I have just clubbed them together into this form. Okay, now one more thing here, rather than x being being a scalar, x could be a vector also. Okay, so x can be a vector, so let me do it for a vector case also. So I'm putting a bar here and let me write x to be a vector with following parameters. So x1 x2 till xn. Okay, so x here is a vector. All right, so if you compare this problem with our earlier one, if you see this problem here, so in this, if you draw the comparison, so fx is the same, x square plus 2x plus 3. So let me write it also. So fx is equal to, in our earlier case, it is equivalent to x square plus 2x plus 3, and fix I had was x is greater than equal to 0. Okay, so I had just one inequality constraint here. You can see I had just one inequality constraint. I did not have any equality constraints. Okay, so first we have to write the optimization problem in a proper format, and then we can proceed to understand what kind of an optimization problem is this. Okay, all right, so let's proceed further. So there could be, so you can, depending on the functions here, how these functions behave, we can classify them into multiple types of optimization problems. Okay, so one kind of an optimization problem could be a linear optimization problem. So in linear optimization problem, your f of x and fi of x and hi of x all are linear. Now, what do we mean by linearity here? How do you prove a function to be linear? So there is a very nice result. Every one of you are familiar with this. So suppose if I write f of alpha x plus beta y, if this is equal to alpha times f of x plus beta times f of y, then the function is said to be linear. Okay, so if your objective as well as constraints are linear, then your optimization problem is a linear optimization problem, and these kind of optimizations problems are very easy to solve. Okay. Now the second class of an optimization problem is non-linear optimization problem. Now obviously, as the name suggests, non-linear means your fx or fi of x or hi of x are non-linear. So one or all of them could be non-linear functions. Okay. Now a special class of non-linear optimization problem is a convex optimization problem. Convex optimization problem. Okay, so this is a special case. This is a special case of non-linear optimization problem. Okay, So which this one we are going to discuss it in our second part. Okay. Now uh, now let me give you some more highlights into how do we define certain terminologies in an optimization problem. So again, coming back to the optimization problem, so what we are doing is that we are trying to minimize a function f of x subject to certain constraints. Suppose fi of x, all these are vectors I'm taking, and this one is hi of x is equal to 0. So this is called as an objective function, and these are called as constraints. Now, what is the job of the constraints? So let's understand this. What a constraint does. Now, you know that every function has some domain where it is valid, right? So every function has a domain where it is valid. What the constraint does is that it defines the domain of the overall optimization problem. So in one word you can write it defines the domain of an optimization problem. So what will be the domain of such kind of an optimization problem? So the domain, let me write domain, this is equal to the intersection of all points. So I goes from, let's say, 1 to m, the domain of FIs. What do you mean by domain of FIs? All x for which fi is less than equal to 0, fi of x. So let me write it more clearly, for which fi of x is less than equal to 0. So this is defined as the domain of fi, and intersection with all i's going from again 1 to p. So we had p equality constraints, domain of hi. Fine. So this is called as the domain of the optimization problem. Again, the domain of HIs are all x for which hi of x is equal to 0. So what a constraint does is that it defines the domain of the optimization problem, and you can write this optimization problem as an equivalent of minimizing fx where x belongs to this domain. Okay, so this domain here, you bring it here. So these two problems are equivalent. Okay, so this is an equivalent problem of this equation. Okay, and this is how you define the domain. Domain is the intersection of all these points. Okay, so now a few terminologies that I'm going to introduce now. The first terminology is a point is feasible. Point is feasible if it lies in the domain, if x belongs to D. Okay, what does it mean? It means that fi of x is less than equal to 0 and hi of x is equal to 0. Again, here I for all the inequality constraints, and here I is for all the equality constraints. Fine. So this is the first definition. A point is feasible if it lies in the domain. Now the second definition is set of all feasible points, So this set is called as a feasible set or the constraint set. Fine. So a point is feasible if it lies in the domain, and the set of all feasible points is called as the feasible set or constraint set. Now the third thing is, what is the optimal value of the function? So optimal value, you can write it to be, let me denote it as P star, which is equal to infimum. Infimum is equivalent to minimization. Infimum of f of x such that fi of x is less than equal to 0. Fi of x is less than equal to 0 and hi of x is equal to 0. So we minimize this function f of x for all of the values of x such that these two conditions are met. So this is called as the optimal value of the function, and the optimal point is the point at which this function attains this minimum value. Okay, so let me denote it as x star, and this is given as, so you can write f of x star is equal to e star. Okay, so at this point x star, your function attains the minimum value. And now this point may not be unique. This point x star may not be unique. How? Suppose you have a function something like this. Suppose a function is here, it attains a minimum value and remains flat for some time and then goes up. So over this period, okay, so over this domain, at all these points x, your function value is minimum. Okay, let me write it as p star. Okay, so this is your set of x stars where your function attains a minimum value. So x star may not be a unique point, it could be a set also. Okay, so rather than talking about optimal point, we can also talk about optimal set. Okay. So I stop here. So in this, let me do a quick revision of what we discussed in this particular class. So we started with the optimization problem, the maximization and minimization optimization problem. We talked about the global and the local minima points. Then we also talked about how we used to figure out the optimal points in such kind of functions. We took the derivative, equated it to 0. We figured out the double derivative. If it is greater than 0, we set the function to attain a minima. If it is less than 0, it is a maxima. Right, and we saw some examples of this. Then we also talked about the constrained and the unconstrained optimization problem. And for this constrained and unconstrained, the constrained optimization problem, we do not know the solution. So we wanted to see how we can find out the solution to this optimization problem. So we understood that, so we talked about the general optimization framework. We talked about a linear optimization problem. If all the functions are linear, then it is a linear optimization problem. And if some of the functions are non-linear, then we have a non-linear optimization problem. Then what the constraint does, constraint provides the domain to the problem that we saw. And then we defined some of the terminologies in the optimization problem. Okay, so I'll stop here. In the next lecture, what we are going to do is we are going to understand the convex optimization problem in detail, and then we'll see the solution of these optimization problems. Okay, thank you very much.